Okay. Uh-huh.
Okay, can I ask?
Sure. Of course.
What is a convex and a concave sequence?
What is a convex or concave sequence of numbers? Or,
Yeah, of numbers, integer.
Yes.
Positive integers.
so presumably it's one like that or like that. I guess. Right. This is concave because this guy's in the cave. That's how you. that's how you remember.
For example, the sequence 0, 1, 1, 1, 1, that is concave or concave?
0, 1, 1, 1, 1, 1. I guess that's concave. Not strictly concave.
But 0, 0, 1, 1, 1, 1, 1, it's not.
0, 0, 1, 1, 1 is, you're right, is neither. Yeah, that's what I would guess the definition is. Yeah. Where did it come from?
For problem of the.
Oh, I see. Okay. I don't remember thinking about that. You're talking about points in the plane rather than integers, yeah. Yeah, so right, so a convex set in the plane is one whose convex hull doesn't have any points in it. So a set is convex. A set of points in the plane is convex if the convex hull contains all the points. Yeah. More questions?
A K1 is just a point, right?
Sorry?
K1.
K1 is just a vertex, exactly. Yeah. So let's draw some K1, K2, K3, K4. More questions? No? Okay. Okay, so remember that there's R of K, the Ramsey number of K, is the smallest number of vertices you need such that any colouring of the edges, if you colour all the edges with two colours, then you can find a monochromatic clique on K vertices. Okay? And we proved last time that this number is at most 4 to the K. And how did we do it? The proof was very easy, actually. Proof, it was just take a vertex. That gives you a partition of the other vertices into two sets, given by the red neighbours, and the blue neighbours. And if there's no red KS, so if there doesn't exist a red KS, and there doesn't exist a blue KT in the whole graph, then here there does not exist a red KS minus 1 or a blue KT, and here there does not exist a red KS or a blue KT minus 1. And so we can apply induction on S plus T to bound the number in here, bound the number of vertices here, and bound the number of vertices here. That gives us a bound on the whole thing. Right? Basically, we lose a factor of 2 each time, because you should think of it as, all right, you've got some red neighbours and blue neighbours, just take the set that's bigger and throw away the rest. So each step you lose a factor of 2. And why is it 4 to the K? Because you can't control if you go into the red neighbourhood or the blue neighbourhood. Right, so this found 4 to the K is very natural. It's that you just pick things greedily. So pick a vertex greedily, go into the better neighbourhood. It could be red or blue. You throw away half the vertices, keep going. After 2 K steps, you've taken K steps of the same colour. And the K steps of the same colour give you a monochromatic KK. Does it make sense? Would you like me to do this again slowly? Who would like me to go through this proof again slowly? Oh, okay. So let's do it again slowly. Do you want me to prove 4 to the k or 4 to the k over root k? I'll do 4 to the k over root k. Let's do it properly. Okay, so lemma. RST is at most RS minus 1t plus RS t minus 1. Okay, where RST is defined as over here. So this is equals minimum n such that for every coloring, the edges of the complete graph with red and blue, there exists a red KS or a blue KT. Right? So what's the proof? So set n equal to RST minus 1. So I guess I should have we've already proved these things are finite. Perhaps we can believe that from the previous class. And let C be a coloring without a red KS or a blue KT. Okay? So we're trying to prove this inequality, this recursion. We define n to be this one smaller than this number because by the definition there must exist a coloring with this property. Is that okay? So just by the definition. Please complain. Please, please, please complain if things are not clear. Okay? If things are clear, it's really helpful if you nod your head all the time. Like look happy. Okay. So this is the coloring that we're looking at here. So pick any vertex. V is any vertex of this coloring. Okay, so V is just a vertex, any vertex of Kn. Okay, this is not even for the set of vertices of Kn, set of edges of Kn. Okay? And this is partition. We're given this coloring, so this vertex has some red neighbors, and this vertex has some blue neighbors. Right? Let's call them A and B. And there's a coloring on A and a coloring on B, right? We're given this coloring of the whole world, so this coloring exists on A. So observations, there does not exist a copy of Ks minus 1 in A. Why is that? Yeah, right. If there existed a red Ks minus 1 in here, then you could add this vertex to it, and you'd have a Ks, a red Ks, in the original coloring. But we assumed that wasn't the case. We picked C, so that wasn't the case. Okay? In whatever. I'm going to maybe I'll try to call it G, the coloring, or something. I don't know. In C. What else do we know? I also claim there does not exist a KT, a blue KT in A. I mean, that one's easier, right? there didn't exist a blue KT in the whole world, so there definitely doesn't exist one in A. Right? So what does this imply? Well, it means we have a coloring of A with no red KS minus 1 and no blue KT. Uh-huh. So if there existed, so if not, so if there existed a KS minus 1, a red KS minus 1 in A, these S minus 1 vertices, everything's red. Yeah, in the original coloring. I mean in the whole universe. Yeah, so perhaps I want to call the whole universe V or something. Is that better? Okay. Right, so so this is big V and this is little v. I hope that's clear. Yeah, sorry, this is very standard notation, I'm afraid. A vertex is little v and the vertex set is big V, and I'll try and make them big and small enough that it's obvious. Right, so this means we have a coloring with these two properties. By the definition of RST, this implies that the size of A is smaller than RS minus 1T. Right? Just exactly the definition. Because there exists this coloring, so the minimum n, so every coloring has this property, must be bigger. Right? It's just exactly the definition. Okay, and it's an integer, so I'm going to write it like this. Okay, the same thing. Is it okay? Right. Similarly, by symmetry or whatever, size of B is at most RS T minus 1 minus 1. Right? But the size of V equals A plus B plus 1. Right? This equals n, by assumption, which equals RST minus 1. And this is at most RS minus 1t plus RST minus 1 minus 2 plus 1. So we're done. Right? We chose the size of V, the number of vertices, to be n, which was chosen to be RST minus 1. So we know that RST minus 1 is equal to A plus B plus 1. Put upper bound for A and B, so just plug them in. Right? Okay. Is it okay? Proof of the lemma? Okay. So now, to deduce the theorem is just a simple induction. So what I'm going to claim, I claim that, let's do another lemma. The lemma is more general than the theorem, actually. RST is at most S plus T minus 1, choose S minus 1. All S and T. It's just induction. Proof. Okay, check it for S equals 1. What is R1T? What is R1T? Right, it's 1 because you don't get to colour anything, and you get a red K1. What else are you going to do for 2? Maybe it's a bit too trivial. Let's do R2. I mean, 1 is whatever. I mean, 1 is also true because it's 1, but okay. R2T? T, right? Is T, which is equal to, no it's not, it's at most T plus 1, choose 1. I mean, even smaller than this. Right, t plus 1 choose 1 is this guy with s equal 2. Okay, so it's true for s equals 1, it's true for s equals 2. Okay, let's do induction. It's okay? Just checking the definition. So s equals 1, 2 is okay. What about the induction step? Well, RST is at most this plus this, right? Which by induction, Portuguese, is at most s plus t minus 2, choose s minus 2, plus s plus t minus choose s minus 1. And who knows what this is equal to? S plus t minus 1, choose s minus 1. Right, it's Pascal's triangle. First time. Right. And now let's finish the proof. R of k equals R of kk. Right, that's what the definition is. Which by the lemma is at most 2k minus 1, choose k minus 1. And okay, that's less than 2k, choose k. I was just being lazy with the minus 1s, and then you're done. Okay, yep.
I find it strange that the bound is not symmetric on S and T here.
Ah, so it should I have a 2 there instead? Ah, sorry, I can have a 2. Thank you. Yeah, sorry, and it worked for here as well, right? I was being silly. Yeah, when s equals 2, it worked. Yeah. When s equals t equals 1, it also works. Thank you. So yeah, this proof was correct, but yeah, you just proved something stronger by pointing that out. Yeah. And here as well. Yeah, thank you. Okay? Okay. Right. How about lower bounds? Anyone manage to prove any kind of lower bound at all for the Ramsey number? Okay, I'll go first. I can prove k. It's at least k. Who can beat that?
$2K.
2k. How do you prove 2k? Seriously, how do you prove 2k? I want a construction. So what's the proof of 2k? Anybody, yeah.
Maybe a bipartite graph.
Uh-huh. Okay, that'll work. Let's do red inside here and blue across. And these better be k minus 1s. Ah, you didn't quite prove 2k, but 2k minus 2. Well, yeah, okay, I'll let you off. Who can improve on that? So you've got a red clique of size k minus 1. How large is your largest blue clique? What's the largest blue clique in this coloring? 2, right? There's no blue triangle. So that seems a bit wasteful. Can you do better? What's a better construction?
Make another copy.
Take another copy. Yes, exactly. Very good. Right? 3k minus 1. Well done. Yes? How far? K minus 1 times. Right. R of k is greater than k minus 1 squared. Right? This is the construction I expected you to find. Right? Your homework is really find this construction and then realize that you're stuck and you can't do any better. Right? So actually, when this problem was first introduced, this was suggested as potentially the correct answer, the extremal answer. And it's pretty difficult to come up with a construction that was better than this. It was only several decades later that someone came up with a construction of size k cubed. So this is not the best thing. So the construction for k cubed I might show you later in the course. It's not trivial. I mean, the definition of it is fairly simple, but proving it works is not completely trivial. I mean, not even easy. This was k cubed. I'm not even sure what decade it is. 70s maybe. And then the first construction that gave something that's super polynomial was in roughly 1980. So it's greater than c to the k to the c, sorry, for all c. There was something like, I've forgotten what, something like k to the root log k. This was it's a famous construction of Wilson. Oh my God, I've forgotten who else it is. So I forget, but we might see this later in the course. Is it Frankel and Wilson? I think maybe it's Frankel and Wilson. Yes. I've forgotten. Oh, well, yeah, it's in the notes. If, so this is pretty hard, right? It's pretty hard to come up with constructions that come. This is nowhere near 4 to the k, right? K to the root log k is nowhere near. Nevertheless, it was proved by Erdös in 1947, I think, that it's greater than root 2 to the k. So how can this be? Why did these people come up with these constructions in 1980, and why are they famous when they have a much worse bound than Erdös proved more than 30 years earlier? There's an obvious answer. It's not a construction, right? We're going to prove a lower bound, but we're not going to construct a coloring. It's very difficult to construct a coloring. We're going to show a coloring exists. Okay? So. So, how do you want to color the edges of the complete graph so that there's no large monochromatic clique, but I don't want you to tell me how to do it? I want you to tell me how to do it without telling me how to do it. Sorry? Exactly. We're going to do it randomly. Okay? We're going to prove this bound by coloring randomly. Okay, this should be surprising. So what does that mean? For each edge, let's just toss a coin, a fair coin, independently for each edge, probably half being red-blue. So the probability that the color of an edge is red should be a half for all edges, all independently. This is independentiamenci. Independentiamenci. Is that right? I always feel like I'm writing it it's way too long. Anyway, I'm going to write in-depth to mean this. Okay, so what do we need? What do we need to show? We would like to show that there exists a coloring with no large monochromatic clique. That's the same thing as showing that in this distribution, the probability that there's no large clique is positive. Okay, so what we want is the probability that there does not exist a monochromatic monochromatic copy of kk should be positive. Okay? That's what we want to prove. If we can prove the probability is positive, that means there must exist one, right? Because we had some chance of finding it. So how are we going to go about proving this probability is positive? It's not really obvious how to estimate this probability. I mean, and in fact, we really don't know how to do it. But we can get a simple bound by using a trick that we're going to use lots of times in this course. And the idea is that when you have some random variable, it can be very difficult to calculate probabilities like this. But there's something that's very easy to calculate. And the thing that's very easy to calculate is the expectation. Right? You can calculate expectations of random variables. So when you want to prove something like this, you should follow these steps. So the first step is to define a random variable that counts the thing that you want to count. Okay? So what is the random variable in this case? So let x be, well, a random variable will always be the number of somethings. It will be the number of somethings in our random object. So in C. What is it we're trying to count? We're trying to count monochromatic cliques, right? We want to know if the number of monochromatic cliques is 0 or not 0. Right? So let's count the number of monochromatic cliques. The number of copies of, sorry, copies has a thing? Yeah. Although it would be copiers, I guess. Okay. Monochromatic copies of kk in C. Okay? This is a random variable, right? It's a number. It's a non-negative integer, but it's a random one. We've got some distribution over the colorings, and given a coloring, this is a function of the coloring. Okay? So it's a random variable. So what's the expectation of this random variable? What's the average of the random variable? Well, so I'm not assuming any knowledge of probability at all, including what expectation is. So how many people are comfortable with using expectation? Quite a few. How many are uncomfortable? Don't be shy. It's all right to be uncomfortable. I was also uncomfortable with expectation, actually, till quite late on in my mathematical career. Okay, so let me tell you a little bit about expectation. Yeah, I think I was reasonably far through my PhD before I was comfortable with expectation. It was quite late. Yeah. But I mean, it's very simple, actually. I mean, it was silly to be scared of it. So what is it? What's the definition? So I'm always going to assume my random variables take non-negative integer values to make things simple. Okay. So it's just the sum over k is 0 to infinity of k times probability x is k. Okay, that's the definition. But that doesn't really help us very much here, right? I mean, how is this going to help us calculate? We don't know the probability that it's 0. That's what we're trying to find out. Well, fortunately, it's got a really nice property. The really useful property that expectation has is linearity. The expectation of x plus y is just the expectation of x plus the expectation of y. Right? And this follows just from the definition. Right? This is the key property. And what is our, and this doesn't, you don't need independence or anything, it's just true always. And what is our x here? Our x, well, you can write it as a sum of random variables that are very simple, that are indicator functions. It's just the sum. So it's the number of monochromatic copies of CK. So it's just the sum over all copies, of KK, of the indicator function that KK is monochromatic. Right? So this isn't great notation. This is supposed to be a copy of KK. Maybe I should write it as H. Is it clear or not? Is the sum over all copies, all cliques of size K, they're just a bunch of things that exist before the randomness, and then each one has a certain, it might be monochromatic or not. And you count 1 if it's monochromatic. So this is just the number of monochromatic copies. Right? So then what's the expectation of x? Let's just use this definition. It's the sum over kk's and kn of the expectation of this indicator function that kk is monochromatic. But what's the expectation of an indicator function? Now we can go back to the definition. An indicator function takes values 0 and 1. So here you get 0 times probability it's 0 plus 1 times probability it's 1. So it's just the probability it's 1. Right? So this thing is equal to the sum over kk and kn of the probability that kk is monochromatic. Okay? That's just what expectation of indicator function is. Okay, so now we know what the expectation is. It's just a sum of things we understand, of probabilities that maybe we can calculate, because instead of it being something weird with like crazy numbers of kk's all interacting with each other, now it's just one of them. What is this probability? Okay, what is this thing equal to? We can say exactly what it's equal to. What's the probability that kk is monochromatic in this coloring, this random coloring? Each edge picks a color independently at random, probability of half. So almost. So it's definitely a half. Half is the probability of the edge being a certain color. There was a guess that it was k minus 1. Not quite. K choose 2. Minus 1. Thank you. Right? Because there's 2 colors it could be. Right? The first edge can be whatever, and the others all have to be the same. K2 is just the number of edges. So that's the probability. The probability that a particular kk is monochromatic is exactly this. Right? Very simple.
Sorry, I don't get why the exponent is...
K choose 2 minus 1. So there are k choose 2 edges in kk, and there are 2 colors it can be monochromatic in. So think of the first edge as being whatever, red or blue. The other k choose 2 minus 1 all have to be that color. So each of those happens probably a half. Or you can think, what's the probability they're all the same color and then have 2 colors? But I think it's easy to. Yeah. So the other k choose the k choose 2 minus 1 of them have to match the other one. Okay? And each is probability a half. And they're all independent, right? The independent tells you can multiply the probabilities. Right? Think 2 random variables being independent means exactly the probability of the 2 things occurring is the product of the probabilities. Right? That's what independent means. Okay? Is it okay? So there's just these edges, each one probability half, and nothing to do with each other. Okay, and how many copies of kk do we have in kn? And choose k. So now we've calculated this expectation exactly. Right? We had no idea how to deal with the probability, but the expectation, we can say exactly what it is. Okay. So if we want the probability of it being 0 to be big, which you want the expectation to be small. So let's try and give an upper bound on this expectation. Maybe I'll make myself a bit more space. So I'll just move this up. I'll move all this up. So sum kk and kn of probability kk is monochromatic equals n choose k half to the k choose 2 minus 1. Okay, so we would like an upper bound on this. So now we have to do some sort of boring, I mean, calling it algebra is a bit unfair in algebra, analysis or whatever. Also unfair in analysis. So we'll do some boring estimation to show it's small. So here's a trick that's useful. An upper bound for n choose k. Maybe I'll stick this, I don't know where. So here is a useful upper bound. Here's useful upper and lower bounds for n choose k. N choose k is at least n over k to the k. And it's at most e n over k to the k. Okay, and this holds always. Okay? And when k is much smaller than n, this is normally a good estimate. Okay? Okay, so if you don't know these estimates, I would write them down, go home, prove them for yourself, remember them. They're useful. Right? You'll need them a lot, in this course at least, if not in life. Okay? So I'm just going to use this bound. So n choose k is at most e n over k to the k. And then here we have a half to the k times k minus 1 over 2. Maybe I'll pull this half out the front. There's 2, in fact. Okay? Okay, that didn't look like it helped us that much, except now we have two different things that are both to the power k. So let's put them together. This is 2 times e n over k, 2 to the minus k minus 1 over 2 to the power k. Right? So just rearranged. And now what do you see? We want to prove that this thing is bigger than root 2 to the k. So let's set n equal to root 2 to the k. Right? And show that this is small for that value of n. And if n, here you have a 2 to the minus k over 2, which is exactly root 2 to the k. So this cancels with this. Right? So this equals, this is if n equals root 2 to the k, or perhaps if you like, if n is at most, then this is at most. E over k, what have we got? We've also got a root 2, e root 2 over k to the k times 2. Ah, but great. Now this goes to 0 very quickly with k, right? This is now in particular, it's less than 1 if k is at least 5, 6, 10 to the 10. I mean, 10 to the 10 I'm pretty sure about. Right, I mean, if it's bigger than, maybe it's 6 or something, I don't know. So we've shown that if n is at most root 2 to the k, then the expected number of monochromatic cliques is less than 1. How do you finish the proof? Why are we done?
Se é menor que 1, quer dizer que a probabilidade de não ter é maior que 0.
Exactly. right? If the expected number is less than 1, the probability that it's 0 has to be positive, right? Because otherwise, it would all, I mean, it's an integer. If it's never 0, it's always at least 1, so the expectation will be at least 1, right? If the expectation is strictly less than 1, it has to be 0 sometimes, right? It's a non-negative integer. This implies that the probability that x is 0 is positive, which is what we wanted. This was Erdős' incredibly simple but incredibly brilliant and powerful idea that just by coloring randomly and calculating the expected number, you can show that this thing exists, even if you can't find it. Right? So this idea, the so-called probabilistic method, this is perhaps the first example of the probabilistic method. This will recur throughout this course and is now a huge area of mathematics. I mean, not just in combinatorics, it reaches into lots of different areas of high-dimensional geometry and, I mean, all kinds of things. This intuition of probabilistic thinking is extremely useful, extremely powerful. This was the first example of it. Does it make sense? I want to make sure you understand this proof. Everyone should understand the proof. So if you don't, please say. We'll see lots of proofs like this that will be more complicated. So this is kind of the basic example. You happy? Everyone happy? Okay. Okay. So, one brief comment that, okay, we could have improved this a bit, right? We could have taken n a bit bigger, so we have this factor of k that we didn't really use. So, okay, so actually this proves something with maybe some polynomial factor in front. Let's not work it out exactly. But what I do want to say is that these bounds that were proved a long time ago, so in 1935 and in 1947, they haven't been much improved on since then. So the most recent progress so 4 to the k over something like, I forget exactly, something like k to the log k. This was proved by Conlon about 10 years ago. So first, Andrew Thomason improved the root k to a k to the 3 over 2 in about 1987. And then Conlon managed to prove the super polynomial factor below. This was a very big breakthrough and it's a very well-known result. But it doesn't improve the 4, right? It doesn't prove 4 minus epsilon to the k. From below, the situation is even worse. So the bound has been improved over the course of, what is that now, 70 years. It's been multiplied by 2. And even that took 2 steps. But multiplying by 2 was not easy, so the proof involves something called the Lovász local lemma that maybe we'll see later in the course. So this is a major, perhaps the most famous open problem in extremal and probabilistic combinatorics, is to improve these bounds. To try and at least beat the root 2 and the 4, show that one of them is not the right constant. There's a reasonable chance that the lower bound is correct. There's basically no chance the upper bound is correct. That would be extremely, extremely surprising. Okay. So I think rather than continuing with Ramsey theory, because the obvious next steps in Ramsey theory are quite a bit more difficult, I think it's probably better if we change topics and do something basic and nice and not too difficult in a similar but slightly different area. So let's move to extremal graph theory. So here's a basic extremal problem in graph theory. Let's define. So I'll jump a little bit between different topics in this course. The idea is to try to demonstrate to you that similar ideas come up in these different settings. That even though each setting might seem a little bit particular, that really these are sort of fundamental ideas that we're uncovering as we go along, and the ideas have very wide application. So sort of any kind of combinatorial or finite object that you look at, similar kind of ideas will appear. Okay. So you should focus more on the ideas and less on the particular problems that we're looking at. Okay, so what's the definition? So remember that we're interested in extremal problems. So what's the most basic extremal problem you could ask about graphs? Well, you could ask how many edges in a graph force a copy of another graph. Now, this guy, it's the maximum number of edges in a graph G. This is the number of edges in G, where the number of vertices is n. Perhaps actually I'll write it slightly differently, such that H is not contained in G, but G is contained in Kn. Okay, so this is the complete graph on n vertices. So it's got n vertices and n choose 2 edges. G as a subgraph means that it's got n vertices and fewer edges. So just some of the pairs are edges. And H is not contained in it means you can't find a copy of H. So let's think of a simple example. Let's let H be the triangle, K3. So what is extremal number of K3? What's the maximum number of edges in a graph with no triangle? So as we saw on Wednesday, the first thing to do is to try and come up with some constructions. Right? Try and think of some graphs with lots of edges and no triangle. And once we think we've got the best one, then we can try and prove it. So give me a graph with no triangle. Once again, how many people know the answer to this question already? Okay, so you guys keep quiet. People who don't know the answer should try and think of some graphs.
Cycle.
So right, a cycle is a graph without a triangle as long as it's got at least 3 vertices. So G is Cn. This has n edges. Okay, so who can beat n?
Lots of C4.
That's another one. G is, so we could take this one also has n edges. Ah, like this. This now has about 4n over 3 edges or something? Something like that.
If you put
So I could draw a C4 like this. Is that what you want me to do?
And you continue.
This is getting like that. Yeah, it seems like a good idea. Why does it not have a triangle?
It's bipartite.
Yes. It's got, right, it's bipartite means that it's got two parts and there's no edges on the top and no edges on the bottom. And any triangle would have to have two vertices in one, so therefore it's fine. So we draw the logical conclusion. Just for all of them, right? Yeah, you can put all those edges in. That's got way more. That's now got n over 2 here and n over 2 here. We've got n squared over 4. It's the same construction we had before. Right. Okay. So that looks pretty good. That's really like, that's like half of all the edges. Seems like a pretty good guess. So let's prove it. So Mantell in 1907 or something proved that the extremal number of the triangle equals n squared over 4. Well, okay, floor. Yeah, so he proved it in the sense that it appeared in some magazine as an open problem attributed to him, and several people solved it by the following week. But anyway, so what's the proof? Well, so there's lots of ways to prove it, but let's think. So what do we want to show? We've shown the lower bound. The lower bound is just a complete bipartite graph. So I'm going to draw a complete bipartite graph in general like this. Okay? The correct way to draw graphs, by the way, unless they're very sparse, is as potatoes. Right? There are various potatoes, and the potatoes are either like dense or sparse or whatever. This is the correct way to think about graphs. Right? Don't think about them. Definitely don't draw your graphs like this unless they're a cycle. Right? Don't try and start doing this or something. I mean, it's just a total disaster. Right? Your graph should look like this. Okay, so we've got a graph. Let's suppose we have a graph with, let's suppose that E of G is strictly greater than n squared over 4, floor, whatever. And we want to find a triangle inside it. So we've got some incredibly complicated object. It's got n vertices, n is huge. It's got half of the edges. So half the edges are present, half are not. It can look like basically anything. It can look like a random graph. It can look very structured. You have completely no idea what it looks like. How are you going to deal with this unbelievably complex object? Grab it, exactly. You have to grab it somehow. And a good idea here, as was suggested, so sometimes you grab things by a vertex. Here it turns out it's nice to grab it by an edge. Okay, I'm just going to grab an edge of this graph. Any old edge, doesn't matter. What does this edge see? Well, this vertex sees its neighbors. The other one sees its neighbors. And then there are some guys who aren't neighbors of either. Right, we get this partition of the rest into 4 sets. What can you tell me about this picture?
The intersection is empty.
The intersection is empty because if there were a vertex here, then you'd have a triangle. Okay? So if we have a triangle, we're done. So let's redraw this picture like this. So this guy has some neighbors, and this guy has some neighbors. Okay. Now, what else can you tell me about this picture? We want to say something about triangles or counting edges or something. So what can you tell me about this graph down here inside this set?
There are no edges.
No. There are no edges inside here or here, but I deliberately tried to point not to that. I mean, sort of, this whole thing. So there might be lots of edges, but there are no triangles, right? For the triangle, we're done. So what is this pushing us? This picture is pushing us to use a certain technique. Yeah, induction, right? I mean, in general, anytime you see a statement that has an n in it and is completely general, it says for every graph with n vertices this, or whatever, every graph with, then induction is sort of a natural thing to try, right? It's sort of set up for induction. Okay, so, right, induction is bad when, you know, if the statement is sort of complicated, it's only true under certain conditions, then when you try to do induction, you'd have to stay in the family, it would be very complicated. But this is totally general, so it makes life easy. Okay, so what can we say about the number of edges in this graph? So this is G. So, okay. Our proof is going to be by induction. Proof induction on n equals 1 is okay. Extreme number is 0. 2, extreme number is 1. It's okay. Should we even try 3? 3 should be 2. That also seems to be good. Okay. So we're good with small cases. Okay. So what does the induction hypothesis tell us here? It tells us the number of edges of G. So if G does not contain a triangle, this picture tells us the number of edges of G is at most what?
I have a question.
Yeah, please.
For n equals 2, it gives 1
Yeah.
as an answer, right?
Yeah.
But with 2 vertices, we can
Have one edge.
Where is the triangle?
yeah.
There's no triangle.
Okay.
It's the maximum number without a triangle.
Ah,
Yeah.
It's complete edges, no vertices.
Yeah. Yeah. It's okay? Okay. So let's call the graph on this vertex at G prime, just for counting things. So the number of edges of G is at most E of G prime plus what? There's the number of edges down here plus the edges between them plus this one. Now, how many edges do you have between these two vertices and the bottom? Right, at most n minus 2. Why? Yeah. Right, each vertex, yeah, the correct way to count is not from the top, it's from the bottom. Each vertex down here has at most one neighbor up, right? And there's n minus 2 vertices down here. Okay, so it's at most n plus n minus 2 between the two sets, plus 1 at the top. Okay, now, how many edges does G prime have? Well, G prime is triangle free. So by the induction hypothesis, this is at most n minus 2 squared over 4 floor plus n minus 1. And for those who can do algebra in their head, we'll see immediately this is equal to n squared over 4 as required. For those who can't do algebra in their head, n minus 2 squared is n squared minus 4n plus 4, which when you divide by 4 is n squared over 4 minus n plus 1. Is it okay? That's the proof. That's it. That's Mantel's theorem. Okay. So, now for another general rule of mathematics. Whenever you see a statement that has a number in it, you should think, can I generalize this? Right? It seems that Mantel didn't think this. And so I had to wait another 34 years before Turan came along and thought to generalize it. So, what is the extremal number of KR? Right? Once again, you should give me a construction. So instead of avoiding a triangle, now we're trying to avoid a complete graph on R vertices. Give me a graph that has lots of edges and does not have a copy of KR. Does not have a clique of size R.
R minus 1 potatoes.
Yeah. So I want to say it again?
R minus 1 potatoes.
Yeah, R minus 1 potatoes, exactly. Exactly. Take R minus 1 potatoes. You stick all of the edges in between them. Right? And nothing inside. This does not contain any copy of KR, because if you have R vertices, you have to have two of them in the same part. There are no edges inside the parts. Right? So V1 up to VR minus 1, and they're all of size n over R minus 1 floor or ceiling. Okay? This is called the Turan graph. And it has, so it's called TRN, and the number of edges is little trn. And Turan's theorem says that this is the best. Right? So this extreme number equals trn, which is approximately, well, how large is it? Each vertex, its neighbours are everybody except its own part. So its number of neighbours is about n minus n over r minus 1. So the density is about 1 minus 1 over r minus 1. So this is roughly 1 minus 1 over r minus 1 times n choose 2. Is it okay? Oh, why? Yeah, sorry. So we have r minus 1 parts, all the same size. So how are we going to count the edges? Well, instead of actually counting them, let's just try and see what proportion of all n choose 2 edges are present. And every vertex is the same, so it's enough to look at a single vertex and say what proportion of the other vertices are his neighbours. And what we see is that his neighbours are everyone in any of the r minus 2 other classes, but not his own class. So the density of edges is r minus 2 over r minus 1, which is that. Did it make sense? I mean, you can also just count the edges, but it seems it seems easier. Is it okay or not? No, it seems not. Where can I write this? Maybe I'll get rid of this. So TRN v1 up to vr minus 1, all edges in between, no edges inside. Number of edges of Trn, the number of edges of Trn is, if you like, so how many pairs are there? There are r minus 1 choose 2 pairs, and each of the pairs is complete, so we get n over r minus 1 squared. So let's pretend that they're all of size n, exactly n over r minus 1. So let's assume that n is a multiple of r minus 1. Okay? So to maximize the number of edges in this thing, you should take the parts as equal size as possible by convexity. Okay? So that's the number of edges. Is it okay? There's r minus 1 parts. Now let's just draw it for 4, because then you can actually see it a bit better. Okay, I'm going to pretend that r is 5. v1, v2, v3, vr minus 1. Okay? And each of them has size n over r minus 1. Okay? So the number of edges is just, you take a complete bipartite on each pair, n over r minus 1 squared, times r minus 1 choose 2, the number of pairs. What's that equal to? Well, it is r minus 1 cancels with 1 r minus 1, you get r minus 2 over r minus 1 times n squared over 2. Right, which is basically this. Yeah?
Why each rotation has a size of n over r minus 1?
So the Turan graph is defined to be the r-partite, yeah, so maybe I should call this r minus 1, in fact. Yeah. Yeah, I think I want this to be, I'm going to call this r minus 1. So it's the right number of parts. So this is the r minus 1 partite graph with the most edges. I want to have as many edges as possible so that I get really the maximum here. And the way to maximize it is to take them the same size. If you took it very unbalanced, you'd have fewer edges, which you can see just by convexity. It's by
Yeah.
yeah.
Got it that each potato must have the same size, but why do they have, like, couldn't we pick like r minus 2? Wouldn't that be big?
Oh no, it'd be smaller. Yeah, so if you fewer parts, then it's smaller. And so how do you see that? Let's compare this guy with this guy.
Yeah, but I mean the size of each circle. It's n over r minus 1. I'm asking why we are picking r minus 1 and not like r minus 2.
If you took r minus 2 parts, if you took fewer parts, then you'd end up with fewer edges, because your degree would be, your density would be 1 minus 1 of r minus 2 instead.
Yeah. Would we have a click then?
No, you wouldn't have a clique, but you'd have fewer edges. It'd be a worse example. It would still avoid kr, but it wouldn't have as many edges. Right, so if you want to avoid k4, then these are 2 of your choices. But this one has about n squared over 4 edges, and this one has about n squared over 3 edges. Right. Okay. So let's try and prove Turan's theorem. So how would you like to prove Turan's theorem? So another general rule in mathematics, or general sort of idea, if you have a proof that works in a particular case, then why not try to generalize that proof before you come up with a totally new proof? Right? So we have a proof that works for r equals 3, so let's try it. Let's see what happens. Let's try induction on n. N equals 1 up to well, 1 up to r minus 1 seems pretty safe. Right? Because then, if n is at most r minus 1, you just take a clique, and the Turan graph is also a clique. So fine. Okay, suppose that kr is not contained in G, then what should we do? So last time we decided to grab this graph. We got this very complicated graph. We tried to grab it by an edge. What should we grab it by this time? It's a very good idea. Let's grab it by a copy of kr minus 1. What if there are no copies of kr minus 1? There are definitely no copies of kr.
And you can add edges and you get a copy.
Yeah, so that's a good idea. So one thing would be that it's not maximal, so add edges until it's maximal, then you've got a copy. Another thing you could do is say, all right, well, let's use induction on R. We've got some strong condition. If there's no R, kr minus 1, let's prove for r minus 1 instead. Okay, either way. Okay, so let's suppose there is a copy. What does it see? It sees its neighborhoods down here. Let's call this thing G prime. What do we know about G prime? There's no kr. That's all we know about G prime. There's no kr. And it's got n minus r plus 1 vertices. Maybe I want to do this for r plus 1. Sorry, I think I may want to do this for r plus 1. Maybe it makes life a bit easier. So I think I should have done this in the first place. Yeah, so I'm just going to add 1 to r everywhere. And then this is n minus r. Sorry, I think it just makes the numbers slightly nicer. Okay. So, the number of edges in G is the most number of edges in G prime plus what? Yeah, so each vertex here, again, we should say, how many neighbors does this vertex have up here? Oops. Right, it can't have r neighbors up because then you'd have a kr plus 1. So it has at most r minus 1. So it's at most n minus r times r minus 1 plus the guys on top plus r choose 2. Okay. That's at most what? By induction, number of edges of G prime is at most Turan of r n minus r. Plus n minus r minus 1, plus r choose 2. and I claim that by magic this equals TR of n. Now, how to justify the magic? Well, I mean, one way is just to write it out algebraically, write out the exact function of the number of edges and check it, which you can do. But that's kind of boring. So let's try and prove it by picture instead. Okay, why is the difference between TRn and TRn minus r exactly this? Well, what's the difference between these two graphs? We've added r vertices, and we know they're both r-partite graphs, with class sizes equal as possible. So we've added one vertex to each class. Okay, so we can look at, let me draw it in like this. So if this is the Turan graph TRN, to get this guy, we just remove one vertex from each class. Let's count how many edges we remove when we do that. Well, we remove R choose 2 between them. That's this guy. And for each one of them, we remove to all of the other vertices. What am I saying?
How many potatoes there are?
Sorry? There are potatoes. Right? Because now we're avoiding, sorry, KR plus 1. Sorry. Aha. Ooh. That was right. Hope so. Each vertex, how many other edges are removed from this guy? So from every other vertex, there are n minus r other vertices, and each one had an edge to r minus one of these guys. So that's exactly this, and so it's true. Okay? So the proof, there's no algebra at all, it's just a picture. Is it okay? Right? So there are r choose 2 edges, so you remove r vertices. By the definition of the Turan graph, it's one vertex per class. There are r choose 2 edges between them, because they're in different classes. And every other vertex is incident to exactly r minus one of them, all of them except for the one it's in its own class. Okay. And that's the proof. It's like 3 lines. Okay. So, it's made quite good progress. What about other graphs? So we've done clique so far. Suppose we want to try and understand this function, and cliques are very easy, right? So it's a sign that we're not trying something. We should try something harder. What other graphs should we think about? What's a natural question for how do you take this further? Well, perhaps the next simplest graph you could think about is this one. Right, we did a triangle, we did a clique. Maybe that's the next simplest thing, I don't know. What should the extremal number of that thing be? So let's come up with a construction. What's the... Can you give me an example of a graph with no cycle of length 4 that has, I don't know, constant n squared edges? Right? All of these numbers were constant n squared, right? Even for the triangle, it was n squared over 4. Can you get n squared over 1,000,000? Sorry? 3? Oh, complete. Sorry. This is a suggestion. Who can find a copy of C4 here? There it is. Yes, this is a problem. Right? We're not allowed to take these complete bipartite graphs because C4 is bipartite. You can fit it in this bipartite graph. Yeah, so you can do order n with no problem, right? You could just, right, to get a linear number, then whatever, take a path. There you go, there's a linear number. Yeah, you've got a bunch of triangles together, but right, okay. So doing any kind of order n, I'm not so excited about. Can you do something that's better than more than 1,000,000 times n? Then, if you can't do n squared over 1,000,000, can you do 1,000,000 times n? It's also not so easy. So basically, we have no idea. This is okay. At the moment, we have no idea what to do. We tried to come up with constructions. We completely failed. Okay, so let's try and prove something instead. So let's try to prove this is really a theorem Erdös from 1935. The extremal number of C4. Well, we couldn't come up with a construction. We couldn't even come up with a construction that beat linear, that was superlinear. So let's at least try and prove that it's subquadratic. Right, let's try and prove it's little o n squared. Okay. Oh, sorry, this one?
No, the little
Oh, little o, thank you, sorry. Right, f of n is little o of g of n if and only if f of n divided by g of n tends to 0 as n tends to infinity. Yeah, so smaller than any constant times n squared. Yeah, thank you. Please tell me whenever I use a piece of notation that you don't understand, even if I've said it before, please tell me, just tell me to remind you. Okay. How might we prove this?
Can we compare it with the number in which we have K4?
The number we have K4 is like n squared over 3 or something. So it's much bigger. So we want to show that even way before you get even a triangle, already you get a C4. Want to go? Okay, no chance of guaranteeing a triangle, nevertheless, and guarantee a C4. Okay, so should we use induction? That doesn't really seem to fit with little o n squared so well. Right? So okay, maybe that's not such a great idea. You want to look for odd cycles. So you're not going to be able to you're not going to be able to guarantee that there exist any odd cycles because in this graph there don't exist any odd cycles. And it's not really clear that there not being odd cycles tells you very much. I mean, maybe it might tell you, you might think that you're bipartite or
Não,
something.
se todos os ciclos forem ímpares, aí não pode ter um ciclo.
Oh, true.
É tipo, uma
So you want to
geral.
try to avoid all even cycles instead of just C4. Right, that's a much stronger condition.
Sim.
Yeah, with a very different answer. Yeah, so it's, yeah, so you're right, that's a more helpful condition because really you can prove something much stronger. Yeah, yeah, so I don't want to assume anything that strong. So I think it's really, really not obvious what to do. Right? You really need a clever idea. And once again, so like in the previous Erdős proof that you saw, it was a very surprising and very simple idea to color randomly. Again, it's being Erdős, this is a very, very simple and beautiful idea that we've got this extremal result that we're trying to prove, and we're going to prove it by counting something. So I told you that one of the themes of this course is going to be the interaction between extremal results and counting results and probabilistic results. So here's an example where you prove that something exists again by counting something clever. And so the proof idea is we're going to count cherries. And what is a cherry? That's a cherry. I think it's an extremely non-obvious thing to do. I'm going to count them in two different ways. So, how many cherries are there in a graph? I would like two bounds. I would like one that says, yeah, maybe I should do it this way around. I would like a formula for exactly how many there are, and I would like an upper bound. And I'd like to do this by counting in two different ways. So what are the two obvious ways to count cherries? Yeah, you count from the top or the bottom. Right? So yeah, let's count from the top. That's a good idea. I suppose we're counting from the top. So how many are there?
Depends on the degree of it.
Exactly. So how many are there as a function of the degrees?
E choose 2.
Right. So given this vertex, there's the degree choose 2. So the total number in the graph is just that summed over V. Exactly. So sum over V in V of the degree of V choose 2. Exactly. Actually, maybe I should. So I mean, it's nice to have inequalities this way around, but I think actually I'm going to continue this. So let me do it the other way around. Is equals the sum over V in G of D of V choose 2. Okay, and how about the other way of counting? I'm going to count from below.
And chooses 2.
Right, and why?
Because you can have 2 cherries with the same.
Exactly, if you have 2 cherries with the same base, then you have a C4. So if there's no C4, then you have at most n choose 2.
Sorry, can you repeat that?
Right, so we're going to count cherries from the base. And the observation is, if there are 2 cherries with the same base, then this is a C4. So if there's no C4, there's at most 1 cherry per base, and there are only n choose 2 bases. So if there's no C4, there's at most n choose 2 cherries. Okay, so we have 2 bound. So n choose 2 is at least this. So we have in some way an upper bound on the number of edges, but it's encoded in this degree sequence in a weird way. So we'd like is a lower bound on this in terms of the number of edges. So how are we going to do that? What is the sum of the degree choose 2 at least? So this is now basic analysis or something. How do you minimize a sum of squares? Yeah, make them all the same, right? So by convexity, this thing is minimized by taking all the things the same. So this is at least n times 1 over n times the sum of the degrees choose 2. This is by convexity. Where, okay, this might not be an integer, but you can define this anyway, right? And what's this thing? What's the sum of the degrees in a graph? 2 times the number of edges, right? If you sum the degrees, you count each edge twice, 1 from each endpoint. So this equals n times twice the number of edges over n, choose 2, which is at least, let's sort of forget the constants, it's at least e of g squared over n over n, sorry. Right, so there was really a factor of 4 here and a factor of 2 here, so really I had a factor of 2 to play with. There's also a minus 1 I don't want to think about, so let's just throw away the factor of 2. Let's not worry about it. Okay. Okay, so now what have we shown? The e of g squared is at most n cubed over 2, basically. So in particular, e of g is at most n to the 3 over 2. Right, which n to the 3 over 2 is certainly little o n squared. Sorry.
And is the theorem for 3 over 2 plus epsilon then, instead of square?
Sorry?
Is the theorem valid for 3 over 2 plus epsilon instead of 2?
I mean, it's true for 3 over 2. The boundary proved is n to the 3 over 2, with no little o's or no, I mean, it's really just that. I mean, actually, we proved it with a slightly better constant. Maybe we should have got a half or something. Yeah. But, I mean, okay. Let's not worry too much about it. Right? So what Erdős really proved was this. It's at most, he basically proved it's this divided by 2, at most. Which, okay, you might think, great, but we couldn't even come up with an example that was better than n. But it turns out this is sharp. So there exists an example of a C4-free graph with n to the 3 over 2 edges. I mean, times some constant. The example is a bit weird. It's algebraic. It comes from a projective plane. So you take a projective plane. If you don't know what a projective plane is, don't worry about it. It's got points and lines, and your vertices are the points and the lines, and there's an edge if a point intersects a line, or if 2 lines intersect, or something like this. It's some nonsense. Anyway, it's some algebraic thing. So this turns out actually to be a fairly general phenomenon, that in extremal graph theory, algebraic constructions come up quite a lot. They'll seem to be often the best thing, and they're very difficult to find. Right? You should, I mean, it's not at all obvious that one should try a projective plane here. For C6, then it turns out you need some more complicated algebraic construction, but these things are very strange. Okay. So we still have 20 minutes. So this gives us time to try and come up with a general theory of extremal graph theory. So what's going on here? So for the cliques, you have this order n squared. For C4, you have this much smaller behavior. So can we try to understand when this happens? So maybe I'll leave this. So question. For which graphs do we have that the extremal number is order n squared? Sorry, the theta means between two constants times n squared. So because it's always at most n choose 2, I really just mean at least a constant times n squared. So in this case, it means there exists a constant depending on h, such that you're always at least that constant times n squared. Though we'll see that the constant doesn't depend on h. Okay. Any conjectures? Any guesses?
Graphs of high degree.
So a triangle has this property, right? Sorry? Right, so it should be the denser the graph, the larger the extremal number. So that's a natural thing to try. Maybe try and give a construction. So can you give me a construction with order n squared edges that avoids lots of graphs? And the hint is yes, you can. Yeah, exactly, right? So just take, if you take a, let's do this around. Take a complete bipartite graph. That has n squared over 4 edges. And it avoids any non-bipartite graph. So any graph that doesn't fit in here. Right? So it avoids a triangle, it avoids a cycle of length 5, it avoids lots and lots of things. Right? So if h is contained in this, this is true. This is the definition of h being bipartite. Right? So a graph is bipartite if and only if you can partition the vertices into 2 parts, so there's no edges in either part. So what does this say? This implies that the extremal number h is at least n squared over 4 for all non-bipartite h. So if every h that doesn't fit in here, just by this example, the extremal number is at least n squared over 4. So can we show that this is if and only if? Can we show that the extremal number is little o n squared for every bipartite graph? So, theorem. Sure exactly when this was. 50s maybe? Okay. So I left Erdős' name up there. Erdős proved this for C4, and then these guys extended it to all bipartite graphs. But the proof is basically the same. So why is the proof the same? I want you to prove this using Erdős' proof, which is just there on the second slide or whatever. Right? This is not a difficult theorem. So what does H bipartite mean? It means you can partition the vertices into two parts such that all the edges go across. So in particular, where's a good place to write? Maybe here. So if H is bipartite, that means H looks like this. There are two parts, and the edges go across. In particular, H is contained in this graph. H is contained in the graph KST like that. S vert is here and T here. Right. And this means that the extremal number of H is at most the extremal number of KST. Right? Because if KST is bigger, so if you avoid H, you definitely avoid KST. Right? So any construction of H also works for KST. So KST just means the complete bipartite graph with part sizes S and T. So let's actually prove, let's bound the extremal number of KST. Noting that K22 equals what? C4, right? K22 is just another name for C4. Right? This is K22, C4. Right? They're the same graph. So once again, if you want to prove something in general, and you have a proof for a particular case, why not try generalizing it? So, there it is. What do you want to do? Count cherries. Exactly these cherries?
With a bigger base.
Aha. Good idea. Let's count cherries with S cherries on them. Okay, so how many are there? How many S cherries are there? likely. And at most, how many are there if there's no KST? Almost. I didn't quite leave myself enough space. N choose S bases, and each one can have as many at most t minus 1. Apologies. Right, this guy is at least by convexity. This is also convex. This thing to use S. Which is this thing to use S. Which is at least this to the S over n to the S minus 1. Maybe I've got to put an S factorial or something stupid here. Okay. Some constant. Whatever. So what have we proved? This implies that.
So we codificate the last
I did this to the S. So I use this n choose k as at least, well, n to the k over k factorial, I guess. Is it true? Well, it's certainly n over k to the k. Should I put s to the s here to be that happier? I mean, I don't care about constants. Is it okay? So what does it imply? This guy is at most this guy. Let's just forget all the constants. Who cares? E of g to the s is at most up to some constant factor. Maybe I'll stick it here. N to the 2s minus 1. So E of g is at most c to the 2 n to the 2 minus 1 over s. So this thing is at most c times n to the 2 minus 1 over s. So we're done, right? Because this is little o n squared. Yeah. Before I forget, I've already forgotten, I was supposed to get all your email addresses today. Maybe I'll go and steal a piece. I didn't bring a piece of paper either, or a pen. Okay, let me go and grab a piece of paper and a pen. Because are you a piece of paper and a pen? Okay, so could everyone write their email address on a piece of paper? So it always happens that I can't read about half of them. So please use capital letters. Right? You're mathematicians, and that, not by definition, but often is correlated with having terrible handwriting. So certainly I have terrible handwriting. So. Yeah, so I'll send you, if you put your email here, I'll send you the first example sheet over the weekend. Okay. Okay, so on Monday, perhaps we'll take a slight change of tack and do some kind of more basic graph theory. And so perhaps as a warm-up for that, you can think about the following question. So we showed just now that the extremal number of h is little o n squared if and only if h is bipartite. So question, when is the extremal number linear? Big O means at most a constant times, a big O of n means at most a constant times n. Okay, so there are some graphs whose extremal number grows linearly with n, and some grow superlinearly. Can you guess, or can you maybe even prove which are which? Probably you can't prove it, but maybe. But you might have some chance of guessing. So I think it's worth thinking a little bit. Okay, so we'll. So please write your email, and I'll see you on Monday.